Okay, hi, my name is Untitled, and we want to continue with what we've started a few minutes ago. Actually, we were investigating 2D shells with different loadings. So we've done this plain 2D shell first with an external loading, and now we want to look at a 2D shell with a gap, like a hole in the middle. Mm, like a CD, for example, a DVD, whatever, Blu-ray disc. Um, we have a gap there in the middle, and there are different applications for this. For example, even in tunneling, or don't know how is it actually called? Is it like sorry, the I don't have the words right now. I can't remember exactly how it's called. But you basically is forage the name? Don't know. Let's say you have the ground here. Um, okay, and then you basically create a hole here in order, for example, to figure out what's like the level, maybe um man, I'm missing the word. It's called Brunnen, rubbish. Wait, I'm just gonna look it up. Just gonna look up how it's called. Give me a sec. Brunnen. It's called a well. Okay, it's a well. Brunnen. Yeah, so it's called a well. We can use it like to reduce the level of water, maybe, or just to figure out what's the level of water in the air here. So it's a well. And so and when you have something like that, at some point you're gonna have water inside, for example. Okay, and we could say that that water is exercising on the inner boundary some pressure. Okay, in the radial direction, and want to figure out what happens. And the disk here, the medium itself could be the earth that's around the broom, around the well. Okay, and of course we could consider it as if the outer radius was very big or whatever. Okay, just for you to see some application. So it doesn't necessarily need to be an actual shell like with but it could also be, it could be like the lower surface or upper surface of a tank or whatever. It could be like, in some extreme cases, an actual ring, but for ring we have other, or slightly different theories, let's say. So r o for outer radius, r e for I for inner radius, and we want to figure out what happens like at a random position. For example, that's a variable. We know the formulas already for the different stresses. So sigma r equals minus, no, not with the minus, sigma r if with the plus value, and the sigma phi is with the minus value. So this one is minus b divided by r squared plus 2c, and the other one is plus b divided by r squared plus 2c. And we figure out already that the g needed to be equals to 0. So now what happens here? We're going to use the boundary conditions again. What do we know? We know, for example, that at the inner surface here, at the inner boundary, along the inner radius, the inner circumference, we have a compressive stress with the value I'm gonna call it should I just call it P? I'm gonna call it small p. I want to write pi like inner, pi like inner stress. Okay, so that's what we know. What else do we know? In this case, we see that on the outer radius we have no stress. So here are the boundary conditions. And those boundary conditions are basically going to be enough because we need two boundary conditions to figure out what are the value of B and C. In the previous case, B needed to be 0 for the stress to be finite. But here we're not going to have any problem with the stress needing to be finite. Okay. If R were equal to 0, then we would have an infinite stress, but we don't have that case here at all. Because in the middle here we have like a hole. So there's no material here at the position r equals to 0. And the material starts at the position r equal to ri and goes up to the radius r equal to r the radius. Okay, so boundary condition sigma r as the radial stress at the position, I should write it here, r equals to ri is a compressive stress minus pi. Okay, and the radial stress again at the position r equals to ro. Outer boundary here is what? 0. In this case, of course, we could also put a loading there. In this case, it's 0. We have those two conditions. With those two conditions, with those two boundary conditions, we can figure out our two um, integration constants here, B and C. So this first value, what does it mean? We can put it in there. So 1 is equivalent to B divided by RO squared plus 2C equals minus PI, and 2 is equivalent to B divided by O. Sorry, this one was RI, and this one is RO squared plus 2C equals 0. And how do we go about this? At first we can basically do equation 1 minus equation 2. That way 2c is basically gonna disappear. Okay, or another way to do it is just to say, okay, 2c is equals to minus b divided by r whole square. We can just do it that way. So this one means 2c equals to minus b divided by r whole squared. Okay, let's call it asterisk, and we're going to put asterisk in equation 1. Asterisk in 1 leads to b divided by ri squared minus b divided by r o squared equals minus pi. Again, we're looking for b here. So we're gonna factorize b is 1 divided by ri squared minus 1 divided by ro squared equals minus pi. In this way, we can actually find b already. We're just gonna write this let's say, in a more common form. I'm gonna bring those two equations and those two fractions to the same denominator. That is ri squared times ro squared, for example. Ri squared times ro squared. So on this side, we're gonna have ro squared, and on the other side we're gonna have r I squared. Hmm? So basically, we multiply the left fraction times r o squared at the numerator and the denominator, and for the right fraction we multiply times r I squared, and then we could just subtract one from the other. Times b equals minus pi, and then we can send this factor to the other side. B is then equals to minus pi times ri squared times ro squared divided by ro squared minus ri squared. Very good. With the negative value, or we could remove the negative value, then inverse the sign here. Doesn't really matter. That's the value for b. And now that we have a value for b, we can find a value for c. Okay, if this is b, what is c? With asterisks, we can figure out what c is. 2c is minus b divided by ro squared. So c is then minus b divided by 2 ro squared. That is minus b, that means plus pi times ri squared, ro squared minus ri squared. I'm gonna write times ro squared first. This is basically minus b, then times minus 1 divided by 2 ro squared. Okay. Sorry. Wait a minute. I've switched the sign. I've changed the sign already, so we don't need the minus there anymore. I've changed the sign already for b because b was negative and I wrote a positive value here, so I've used the minus already. We just need to divide times 2 ro squared, and you can see what happens. The ro squared just goes away with this one, and we're gonna have a 2 over here in the bracket. So I'm gonna write it. C is then pi times ri squared divided by 2 times ro squared minus ri squared. That's C. Good. We have B and C, and therefore we can write the equations sigma r and sigma phi. And since we figure out what B and C are, don't really know if it's necessary for us to write that right now, but let's just do it. So sigma in the radial direction is b divided by r squared. So this one divided by r squared. Watch out. All the values here are known. The radius, the outer radius, the inner radius, those are given for a specific task. Pi is like the stress inside. If it's like for water, we can just, the liquid in this water, we can just compute the water pressure, or it could be pressure coming from something else. We could just compute it. And yeah, the r here, the r square is the actual variable. So if you want to figure out what happens not just at the boundary but at any random position here um, in the actual medium, in the actual material, then we can just input a value for r. So yeah, do we really need to write this down? I actually don't think it's necessary, but pi times ri squared times ro squared divided by ro squared minus ri squared divided by r squared. So times 1 divided by r squared. This is the actual variable here. All the other values are constant. So plus 2c. So plus pi again, we can actually factorize the pi value, as you can see. Plus 2c, so pi times ri squared divided by ro squared minus r. This is I, not 1. I squared. Yeah. Pi could be factorized, and but you're still gonna have those two terms. So that's the stress in the radial direction, and to figure out the stress in the circumferential direction, this we also have the formula. So what change is just the sign here, and you can see it's basically the same, just the sign here. So it's gonna be plus pi, and the rest is really just the same. Good, and that's it. So we can check the results in the book, same book. So we were doing this case here. Again, here they're using the line stress, like with the unit force per length, and we're using the full, this is like the full stress with force per area. So there might be that H, as you can see here, that comes in play. But apart from that, um, we didn't compute um, the displacement. Okay, we might do that next time because I intend to stop the video after this, but we might do the displacement in another video. Let's check those over here. Okay, this is quite a compact form. It's quite a compact way to write all of those, but you can still see the a squared minus b squared. And what did they call a? A here is like the outer radius. Can you actually see that? I hope you can see that. A is the outer radius, B is the inner radius. So A is what we called RO for outer radius, and B here in the form is what we call RI. So this is a more compact form than the one we have here. So we might need to write it a little bit differently so that we can compare. It's not a big deal. Let's do it for the first one. The only difference is the sign here, so this is really not a problem. Let's do it for the upper one. Pi can be factorized. The denominator here can also be factorized, so the RO squared minus RI squared can be taken out already. What else? RI squared can actually be factorized too. And what are we going to have in brackets? Minus RO squared, RO squared for the first part, and for the second part, we also have the 1 divided by R here, so minus RO squared divided by R squared, the actual variable, plus 1. Because from the second term, we've already factorized everything. So this time, then in the brackets, minus R squared divided by R squared plus 1. And here, what are we going to have? By I, same story, just with the change of sign. The change of sign here. There's no minus there, it's a plus now. So RO squared divided by R squared plus 1. Okay, now we can compare this value with the value from the book. What did we get? R here is our stress Pi, like they call it R. For them in here, it's a line stress. For us, it's like it's like the normal stress. Let's just call it like that, like force per A here for us, and here it's like force per length, but you just need to consider that. So they say that the line stress in radial directions equals this factor times the line stress that's actually applied. Is okay. It's okay. So what are the values? A squared, that's like RO squared. Oh, what do we have here? A is like, oh, we have a problem here, right? We have a problem here. We have, it should be A squared, and A is the outer radius. Okay. Below at the denominator is outer radius minus inner radius. That's okay. Then in the bracket is like 1 minus b squared divided by r squared. B is the inner radius. So yeah, they're basically inverted. Oh my gosh. Okay. Okay, wait. It means I made a mistake here by the factorization, I guess. Let's see. Over here, we factor. What did we factorize here? We factorize ri squared. And that's why we have our O remaining there. It seems fine. Or maybe did the mistake come from before? Oh my gosh, I'm looking at the wrong case. We have the loading inside. Oh my god. Okay, that's why. I guess. We Yeah, what we have done is this case here, not the middle one. We've done the case with the loading inside. So we need to compare with what's happening here. It's a squared minus b squared. As you can see, a is like the outer radius, and that's what we have. Ro squared minus ri squared, a squared minus b squared. At the top, we have b squared at the numerator, and that's the inner radius, ri squared. Yeah. And then in the brackets, we have 1 plus a ratio, and that ratio is always the outer radius squared divided by the actual variable squared. So my okay, there we have a minus one here and a plus. Okay, we seen it. Okay, no, it's fine. It's because in this case here they basically put like a minus. They put a minus there in front. But if we multiply this fraction times minus 1, we're going to have minus on both sides in there. It's not all. It doesn't mean that we've got the wrong value. If you look at the if you look at what they have here, the stress itself, the stress is going inside, but we had a stress that's going outside. So basically, we just need to change this. There R here as stress is minus our value. So we need to multiply the whole thing here times minus to get our values. So here where they have a squared divided by r squared minus 1, in our case, what we should expect is 1 minus a squared divided by r squared for the radial stress for nr. And that's what we have. 1 minus outer radius squared divided by the actual variable, the r squared. Okay. And in the other case, what do they have? They have a whole negative fraction. The rest is positive. And in our case, we're just going to have the whole thing times minus 1. Why? Because our stress is not going inward but outward. So just remove this minus in our case, and that's basically what we've found. And so our values are correct. And yeah, that's it for today. Thank you for your attention, and see you next time.